Hey guys, how we doing? We are almost at the end of chapter 6. I am on page 10 of the notes packet. There's a couple binomial applets that we're going to play with in class, and then followed by that there's this Coke problem. Diet Coke versus regular Coke. We're going to do this experiment in class, but what do you think? Could you taste the difference between Diet Coke and regular Coke? I think that you're probably all thinking, obviously, yes, that's such an easy one. However, I would love to test you and see if you actually could taste the difference. So stay tuned for that. That's not the point. Let's do a little bit of math first. We've got this AP Stats student named Emily, and she is testing her stats classmates, and she's making small samples of each type of soda in identical cups, and she's actually having them taste one after the other in a random order to try to identify which one's diet, which one's regular. And 23 out of 30 people in the class, which is pretty good, made the correct identification. So the first part of this question is a little bit vocabulary and reading based. Explain why x is a binomial random variable. Remember, that means we're going through BINS. So I wrote out all the explanation in terms of BINS, what it stands for, and how it applies to this problem. So just quickly, remember that the B stands for binomial, and what makes something binomial? You either succeed or you fail. It's a success-failure condition, and in this case, you're either guessing right or you're guessing wrong. So that is satisfied for the binomial condition. The I stands for independent, and that means that one person guessing right does not impact the probability that the next person guesses right. The N is the set number of trials. There are 30 people, so we are doing this experiment 30 different times. And from the reading, just remember, if there's not a set number of trials, that's what makes something geometric. So if we were like, oh, we're going to keep guessing until 10 people guess right, then we don't know how many times that's going to take us. It could be the first 10 people nail it, or it could be 11 people that we need to get 10 successes or whatever. So when there's not a set number of trials, remember that's what defines something as geometric, and we'll get more into that tomorrow. The last thing, the S, is the success probability. It has to be the same for each trial. So every single person has a 50-50 shot because they're both tasting both types of Coke, Coke and regular Coke. So the success probability for each one is 0.5 or 1/2, or like I wrote down here, they each have a 50-50 shot. And so remember, the mean and the standard deviation, those formulas are on your formula sheet, and they're actually pretty easy. You probably have them memorized, but the mean of x would be n times p, and remember the standard deviation of x is the square root of n times p times 1 minus p. So go ahead, pause the video, and make sure that you can compute those, and then just check your answer with mine. So here's what the mean and the standard deviation are. The mean, basically out of 30 people, if the probability of guessing right is 1/2, then we expect half of them to guess right and the other half to guess wrong. So the math behind that is 30 times 1/2, but you probably, common sense, you could figure that out in your head. That means we expect 15 people out of 30 to guess right. The standard deviation, n times p times 1 minus p, all in the square root, gives us 2.7-ish. And what that means, remember, is standard deviation interpretation out of 30 trials, because we're doing this 30 times. We expect the number of correct guesses, so like what we're measuring, to differ from the mean. The mean is 15. By about, that about word is important. This number is the standard deviation, and what we're measuring here is the same units as number of guesses that we're doing for the whole problem. And again, on average, make sure you've got that. So very basic standard deviation interpretation. And so letter C is the whole point of this question. Out of the 30 volunteers, 23 of them, remember we expected 15, our actual number was 23, made correct identifications. Does this give convincing evidence, this is like a classic statistical question, that the volunteers can taste the difference? So like, at what point would you say, wow, it's more than 15, I think people really can tell the difference between Coke and Diet Coke. And so here's where we're going to make we're going to use our probability calculations that we've been learning and we've been practicing. And so just remember here that if we are going to answer a question like this, and it gives us all this space, and it's a free response type of question, it's not multiple choice, we need to show our whole like thinking and everything going on in our head. So we're going to follow the state, plan, do, conclude procedure. And so stating what's going on here is I'm going to define this random variable because I'm going to find the probability that x is something. And so this random x can't just appear in my work. So I'm going to define it. X equals the number of correct guesses out of 30. And I've already stated up in letter A that x is binomial. It's approximately binomial with a mean of 15 and a standard deviation of 2.7386. And what I want to find here is the probability. Let me zoom. I'm trying to find the probability that this x is greater than or equal to 23. So what's the probability that I get 23 or maybe even more people that are able to guess the correct way? Let's find the probability of that and see how likely it is that 23 people or more are actually able to guess correctly if they are guessing. And so remember, it's really important to be able to show work when you're doing this. And so probability that x is greater than 23 means that I'm going to first do the probability that it equals 23. And then I'm going to do the probability that it equals 24. And then you can see the pattern. I'm going to put my 3 dots. And I'm ending with the probability that maybe all 30 of them guess right. And so that's the beginning of my showing work. And now you have the choose thing with the probability success with an exponent, and then the probability of failure with an exponent, and we're going to show a little bit of that work, and then I'll remind you how to do that in the calculator. So just remember to find the probability that x is a certain number. That means you don't know which 23 people actually guessed right. Remember that. So out of 30, there's a lot of different ways to choose 23 different people. It could be the first 23, the last 23, or any like weird combination that you can think of. So out of 30 people, choose 23 of them to guess right. And the probability of success was 1/2. 23 of them nailed it. The probability of failure was 1/2. The remaining 7 people sucked at that. Okay, so that's what the probability of x equals 23 looks like. Very similarly, what if it's 24? So now out of 30 people, choose 24 of them to get it correct. And the 1/2 probability, 24 of them got it right. The wrong probability, 6 of them got it right. And you can now see the pattern, so I'm just going to put plus ... And then what's the probability that all 30 of them got it right? So out of 30, choose 30. Yes, I know that that is just 1. And oops, I do not need this P here, my bad. Out of 30, choose 30. 30 people nailed it, and 0 people failed it. So again, this is just 1, this is just 1. It's important to write it so that your work is very clear, but you don't need to actually compute that number in the calculator. So the long way to do that problem would be to do all of those individual probabilities using the choosing and everything in the calculator, but just remember that we have a shortcut. If you go into F5, which is distributions, remember that one of your options in there is Binomial Cdf. And then it's going to ask you for how many trials. And so we're doing this 30 times. It's where you like fill in the boxes and put in the information. What's the probability of success? So you could do 1/2 or you could do 0.5. It's the same thing. And then what's your lower bound and your upper bound? And so in this case, what I'm doing is greater than or equal to 23. So that means my lower bound is going to be 23. My upper bound is 30. But as long as I've shown the work, what you can do is you can write it like this and then just type it into the calculator. You do absolutely need to have this work, you guys. I can't stress that enough. You need to show exactly what these P's are and everything for full credit. You never want anybody to go, where did that number come from? What does this mean? Where did she pull that number from? So just be careful about that. Make sure you're showing all your work. But go ahead, type that into the calculator and make sure you get the same answer as mine. 0.002611. Okay, so that is the answer, and that's the calculator part, and that's actually the easy part. What's hard is that we haven't answered any question yet. The question being asked here is, does this give convincing evidence? What does our answer have to do with answering that question, 0.002? So remember, the classic statistics problem is, once we get an answer, which is the easy part, what does that mean? How does that answer the question, and how can I conclude? Because remember, we stated all the stuff about this question. We planned, and we showed our work, and we planned, and we planned, and then we did, and now we have to conclude. And so this 0.00261, think to yourself, it is a P, which stands for probability. So this is actually a very low probability. And what is it the probability of? What does this mean? It's the probability that 23 or more people would guess correctly. And so maybe that helps us answer this question, is that if this 0.002611 is the probability that if they really were guessing and had no idea, that they guessed right 23 times, I think that that tells us that the volunteers actually can taste a difference, because that's such a low probability if they were guessing. So here's how we're bringing it home, you guys. The chances of 23 out of 30 people guessing right if they actually really were guessing. So what I like to think about is maybe if I were just flipping a coin and I would ask 30 people, do they think it's going to be heads or tails? That is truly a guess. And we would expect our number out of 30 to be about half of the people, or 50%, the probability of guessing right and guessing wrong. It probably wouldn't be exactly 50%, but it would be really close if they really were guessing, like in a heads or tails flip situation. In this case, we got such a low probability here that 23 or more people guessed right. The chances of that happening are so small that that tells us that they probably can taste the difference. And so that's what I wrote here. Since this is such a low probability, it seems like they really do know the difference between Diet and regular Coke. So another way of saying that, that's why I put this or, is our assumption that they couldn't tell the difference seems false because of this low probability. So a couple of different ways to explain that, but make sure that you understand that coming up with this number in the calculator is the easy part. Answering this question is where you really have to think. So we're going to practice a little bit more of this tomorrow. We're going to get into some geometric stuff. Thanks for watching. Bring your questions. See you later.